Hi there, everybody. This is Mr. Schnitzius. I'm one of the A squared I geometry teachers. And for this video, we're going to talk about lesson 2-2 about deductive reasoning. This is the second lesson in activity 2. And what we're going to talk about today is using deductive reasoning to prove that a conjecture is true. So if you think about what we learned in the first part of activity 2, in lesson 2-1, we learned about inductive reasoning. We learned that inductive reasoning is based off of recognizing patterns, drawing conclusions, and making educated guesses. And we learned that those educated guesses are called conjectures. We also learned that in deductive reasoning, just because a pattern looks like it's holding true for a set amount of time, that doesn't guarantee that it will always be true. So what we need in order to prove that a conjecture is true, we need a different type of reasoning. Inductive reasoning is really good for using pattern recognitions to make educated guesses, but to know with certainty that those educated guesses are always true, we need to use deductive reasoning, and we're going to talk about that in this video. We're also going to develop geometric and algebraic arguments based on deductive reasoning. So the first thing we're going to do is look at what a definition of deductive reasoning is. On page 18 of the PDF for activity 2 in unit 1, there's a good introductory couple of paragraphs there, but the basic definition of deductive reasoning that those paragraphs share with us is that deductive reasoning uses statements known to be true to establish the truth about additional statements. So in geometry class during the school year, what we talk about a lot of the time are TV shows that use deductive reasoning. So a very popular type of TV show today is all the crime shows on TV. So you might be a CSI fan, or you might be a Criminal Minds fan, or you might be an NCIS fan. And these shows, or detective work in general, are really good examples of deductive reasoning. So the investigators, use statements that they know to be true. Those statements might be, this suspect is known to be in this location at the time of the crime. Well, that's an important fact, but that might not be enough to prove, to know with certainty that that suspect committed the crime. But then you might say, okay, the suspect was in the location that the crime was committed, and we have these 3 witnesses that say they saw him do it. And so now you're thinking, wow, that's more evidence. It's looking more likely that this person did in fact commit this crime. And so then you say, we still need to prove it. It needs to be so convincing that in a court of law there would be proof beyond a reasonable doubt. So maybe you look for some additional evidence, like the person was at the scene of the crime at the time the crime happened, and these 3 eyewitnesses say that they saw the witness do it, but also we found the suspect's blood on the weapon that was used to commit the crime, and we ran their DNA, and their DNA, the DNA on the weapon matches the DNA of the suspect. Well, that's a lot of evidence, and we are taking all of that evidence and putting it together to prove that the conjecture, this suspect committed the crime, is a true conjecture. Those are the type of things that lawyers do, right? So if you're thinking about being a lawyer one day, whether that's a criminal defense lawyer or a prosecuting lawyer, deductive reasoning is really, really important. And it doesn't just have to be important for the investigator. Like, let's say that you're a criminal defense attorney and you're hired to defend somebody that's accused of a crime. And maybe you charge them a lot of money because they're really in a tight spot and they really want to make sure they go to jail. So you stand up and you say, "Ladies and gentlemen of the jury, my client here is innocent because they just look like such a nice person, right? They don't look like they would ever hurt anybody." And if you say that, you're going to get fired very, very quickly. You need to have deductive reasoning. You need to have evidence that you can use to convince and prove to the jury that your client is innocent. So that's kind of a real world motivation for why deductive reasoning is important. Here's a geometry example, since it says up here that we're supposed to understand how to develop geometric arguments based on deductive reasoning. So let's say here I've got angle 1 and angle 2. You learned in activity 1 how to name angles. And you have some given information. We're told that angle 2 measures 43 degrees. And we're told that the measure of angle 1 measures x degrees. And we want to find out what the measure of angle 1 is. Well, in deductive reasoning, you start with something that you know is true. Okay, we know that angle 1 and angle 2 form a linear pair. Why is that? Well, in activity 1, you learn the definition of a linear pair. A linear pair of angles are supplementary, so they have two measures that add up to 180 degrees, and they share a common vertex and a common side. So right there, we can see that common vertex and we can see that common side that this ray is forming right here. Okay, so that's a given fact. That's a starting point. And now we can use that starting point to add on additional statements to solve the algebra puzzle for what the measure of angle 1 is, for how many degrees x degrees is. Okay, so if it's true that angle 1 and angle 2 are a linear pair, because of the definition of a linear pair of angles are always supplementary. So then we would think, okay, what do we know about supplementary angles? Those are two angles whose measures sum to 180 degrees. So if this first statement is true, then it follows that the measure of angle 1 plus the measure of angle 2 has to equal 180 degrees. That's because we know what the definition of supplementary angles is. Okay, so if that's true, and it's also given to us that the measure of angle 2 equals 43 degrees, we can substitute 43 degrees for the measure of angle 2, and we can also substitute the x for the measure of angle 1. So this second line and this third line are really showing us the exact same thing. It's just we're using the given information to change the equation to make it easier to solve. And lastly, we can get that the measure of angle 1 equals 137 degrees by subtracting 43 degrees from each side of that equation. So this is an example of deductive reasoning. Based on the rules of logic and what we know from previous definitions, if this first statement is true, based on the picture that we were given, then the second statement has to be true. If this statement is true, based on the given information, then the third statement has to be true. And if this third statement is true, based on what we know about how equations work from Algebra 1 class, then the fourth step has to be true. So later on, we'll use deductive reasoning to perform what are called two-column proofs, where for every statement we have a reason. We have the why we know this statement is true over here in a separate column. But for right now, we just want you to understand that when you have a situation where you're proving that something is true based on logical reasoning, that's an example of deductive reasoning. Okay, so before we look at some examples, here are two more definitions. We just saw an example of a proof. A proof is the conclusion reached through deductive reasoning to validate an argument. So think back to the courtroom example. A proof uses deductive reasoning to validate that this person committed the crime, or to validate, to show why we should believe that my client is innocent if I'm a defense lawyer. So we can use proofs to know for sure that conjectures are true. And if a conjecture is true, it changes from a conjecture into a theorem. A theorem is a statement that has been proven to be true. And whenever you think of the word theorem, you might think of the Pythagorean theorem that you saw in your middle school math class. A squared plus b squared equals c squared. Well, how do we know that a squared plus b squared equals c squared anytime we have a right triangle? It's because we can use deductive reasoning to prove that that equation is true, not just for the first couple of right triangles that we see, but for any right triangle that we see anywhere, where A and B are the two leg lengths and C is the hypotenuse. So a proof transforms a conjecture into a theorem. And here's kind of a neat flow chart that you can use to see that. Let's say we had a bunch of different right triangles. Let's say you had a 3, 4, 5 triangle, and then you had a 5, 12, 13 triangle, and you had an 8, 15, 17 triangle, and you worked out the Pythagorean theorem for those 3 triangles. And using inductive reasoning, you could make a conjecture. You could say, it looks like the sum of the squares of the 2 legs for these 3 triangles equals the square of the hypotenuse. That's a conjecture. It looks like a squared plus b squared equals c squared for these first 3 triangles that I tried it out on. But we saw in the inductive reasoning lesson, just because a conjecture is true for a while doesn't mean that it is always true. So to prove the Pythagorean theorem, we would need to use deductive reasoning. It turns out that you can prove that a squared plus b squared equals c squared for any right triangle. So that's why we don't just call it the Pythagorean guess or the Pythagorean conjecture. It's a Pythagorean theorem because you can use deductive reasoning to prove that that is true. And we'll do that later on in this class. Let's say we use deductive reasoning to find a counterexample to that conjecture. Well, now we know that that conjecture is false, so now we need to go back to the inductive reasoning drawing board and try to find a conjecture that does work for this situation. So we're going to spend the rest of this video just looking at some examples from the book, trying to choose between whether or not inductive or deductive reasoning is used for a certain scenario. This is number 13 in activity 2. This is on page 22 of the PDF. So this says Todd knows that 3, 5, 7, 11, and 13 are prime numbers. Based on this evidence, he concludes that all prime numbers are odd. So first, we need to think about what a prime number is. A prime number is an integer which only has 2 factors, 2 numbers that you can divide that number by evenly with no remainder. So those 2 factors would be the number itself and 1. So for example, 3 is a prime number because there's only 2 whole number factors for 3. 3 is a factor and 1 is a factor, and that's it. So part A says, is this an example of inductive or deductive reasoning? Explain. Well, to answer that question, we need to kind of think of another question. Is Todd making this conjecture that all prime numbers are odd based on a pattern that he's noticed, or based on proving something using logical reasoning? And it looks like it's based on a pattern, right? I've got 5 prime numbers here. They're all odd. So my guess is going to be that all prime numbers are odd. So yes, it is based on inductive reasoning because it's based on the first, or on several prime numbers, but he has not proven that this is true for all prime numbers. So Todd's reasoning is inductive rather than deductive. So is Todd's conclusion correct? If this is a correct conclusion, this all right here is a very sticky word, right? Not most of the time, not just about all the time. All means all, right? So if we can find just one prime number that is not odd, if we can find one prime number that is even, then we will show that Todd's conjecture is false. And it turns out that there's only one number that we can use to do that. 2 is the only prime number that is not odd. But all we need is that one counterexample. 2 is a prime number, but it is even, not odd. Therefore, not all prime numbers are odd. So we talked in the activity 2-1, with inductive reasoning, it's easy to make conjectures. It's hard to prove that those conjectures are true. It's much easier to show that they're false. All right, number 14. Shayla knows that all rectangles have 4 right angles. She also knows that figure ABCD is a rectangle. She concludes that figure ABCD has 4 right angles. All right, so let's kind of draw out a picture of what Shayla's doing here. So she's saying, all right, I know that rectangles have 4 right angles. So if this is figure A, B, C, D, we'll learn later on that we name polygons based on their vertices. If this is figure A, B, C, D, and she knows that this is a rectangle, then she concludes that figure ABCD has 4 right angles. Well, is this based on a pattern? Is this based on seeing a lot of rectangles and making a conclusion based on the pattern, or is this based on logical reasoning? She's taking these first 2 statements and combining them together to make a conclusion. So that's an example of deductive reasoning. Shayla's conclusion is based on a proof. So her reasoning is deductive rather than inductive. And let's kind of trace through what she's saying here to see if it's correct. She knows that this is a rectangle. If it's a rectangle and all rectangles have 4 right angles, well, then this figure must have 4 right angles. That's the right angle symbol. I'm going to go back and make sure that that one looks like it's really in the corner where it belongs. So, is she correct in concluding that figure ABCD has 4 right angles? Well, if it's a rectangle and every rectangle has 4 right angles, then this quadrilateral should have 4 right angles too. Shayla's conclusion follows logically from the statements that all rectangles have 4 right angles and that figure ABCD is also a rectangle. So now we're going to look at how to use deductive reasoning together with what you did in algebra class to do an algebraic proof. Use deductive reasoning to prove that the solution of the equation x minus 5 equals negative 2 is x equals 3. And we're going to look at what this means when it says be sure to justify each step in your proof. So pretend you were in Algebra 1 class and your teacher said, all right, you're going to solve this equation, but you're going to show all your work. It's the same type of thing here, but we're going to show our work and explain why we know that each step is true. So I rewrote the original equation, but I'm going to put out here that that is the given equation. It's kind of like, imagine solving a problem in your algebra class, but instead of just showing the work over here, out to the side, you have to explain why you're writing what you just wrote, okay? So what would we do if we were in algebra class to solve this equation? Well, we want to get x by itself. So we need to undo what's happening on the left side of the equation to get the x by itself. So how do we undo subtracting 5? What's the inverse of subtracting 5? Well, the inverse of subtracting 5 is adding 5. So we're going to rewrite the original equation, but we're going to add 5 on the left side, and we're also going to add 5 on the right side. That's the golden rule of algebra, right? What you do to one side, you have to do on the other side. But we're not just going to write what you do to one side, you have to do it on the other side. That's a lot of words. Simpler way to say that would be saying that we used the addition property of equality. And if you're looking at this and saying, I've never heard of the addition property of equality before, well, in an activity that's going to come later on, you're going to get a full list of all the properties of solving equations that you need to know for this class. But the addition property of equality is basically a short way of saying if we add the same number to both sides of an equation, the value of that equation stays exactly the same. Okay, so now we are going to simplify this equation. Negative 5 plus 5, that's 0. So we can put x equals 0. Negative 2 plus 5, that's 3. So what did we do to change this step in the equation to this step? All we did was we simply added. So our justification for that step is just going to be addition. And now, well, x plus 0, that's the same thing as x. So we were trying to show that x equals 3. We did it. We showed that x equals 3. But remember, we need a reason. The reason that we're going to put is the identity property of addition. Basically, anytime you see an identity property, that means that you're doing some operation that does not change the value of your expression. For example, right now I'm going to add $0 into everyone's bank account. Bam, I just did it. Okay, but adding $0 to your bank account keeps everything the same. Sorry about that. So before we look at one last example, just some helpful deductive reasoning proof tips. Every time you see a proof like this, you always want to start with the given. You have to know where the starting point is. So your first justification is always going to be that something is given. Your last statement that you are trying to prove is always the last statement. So you always want to start at the beginning with the given equation or the given information, and then when you get to the end, you want to stop because there's really not anything else I have to show here. I was trying to show that x equals 3, and I did, so I'm done. I just need to be sure that I say why this last statement is true. All right, so one last example where we have to choose between inductive reasoning or deductive reasoning. Hairs found at a crime scene are consistent with those of a suspect. Based on this evidence, an investigator concludes that the suspect was at the crime scene. Is this an example of inductive or deductive reasoning? Okay, every time we work this problem out in class during the school year, my students are always like, oh yeah, I remember Mr. Schnitzius said CSI and NCIS and all that. That was deductive reasoning. This person's an investigator, therefore it must be deductive reasoning. Okay, but we have to think for a little bit. Let's make you the suspect. Okay, let's say you have brown hair. All right. So this problem can be tricky because sometimes students aren't really sure what it means or what it means when it says hairs found are consistent with those of a suspect. That would be like, all right, you're the suspect, you have brown hair. I found brown hair at the crime scene. That means that you were at the crime scene. is that deductive reasoning? Have they really proven that you were at the crime scene, or are they just basing it off of a pattern that they see? I see a relationship here between your hair color and the hair color at the crime scene. Since they're not proving that you were at the crime scene, this is an example of inductive reasoning. The evidence shows that the hair could have come from the suspect, but in order for it to be deductive reasoning, we need to have a proof. We have not proved that the hair is the suspect's or that the suspect was actually at the crime scene. So that means this is an example of inductive reasoning instead of deductive reasoning. Okay, so I hope that you've understood the differences between inductive reasoning based on pattern recognition and deductive reasoning based on using logical reasoning to prove that statements are true. If you have any questions, feel free to join one of the question and answer sessions, and we really appreciate all of your hard work. Thank you so much.